Good. Okay. So firstly, thanks to the organizers. It's my first time visiting this institute. It seems absolutely amazing. I grew up in India. I spent 18 years here before leaving. And it's nice to come back to and then do something that's not fight with my parents at home. So I'm happy to be here. Okay, so my goal in these lectures is to give you some kind of introduction to Gromov-Witten theory and the moduli space of curves and intersection theory on the moduli space of curves. And this is kind of a beautiful subject. So the intersection theory on the moduli space of curves, I guess, is what brings together a lot of the people, certainly the mini courses, and then a lot of the people next week as well. And so the way I'm going to try and pitch this is that it's really Gromov-Witten theory in service of the moduli space of curves. That's the perspective I'm going to take. So my perspective is from an algebraic geometer, but I'll try to be somewhat broad in my in the kind of approach we take. So the starting point for me is just the moduli space of curves. Okay, so let's start there and discuss MG. So MG is maybe as a set just the set of genus G Riemann surfaces, genus G algebraic curves, smooth projective algebraic curves. And at least, I think there's some argument that this is one of the fundamental objects in modern mathematics. So it comes up, for example, in group theory via the study of the mapping class group. It's a K-pi1 for the mapping class group. It comes up in algebraic topology because it's a classifying space for the diffeomorphism group of a surface. And this is a sort of reflection of this fact that we all learn, or maybe many of us learn early on, about the fact that a hyperbolic, conformal, and complex structure on a Riemann surface or on a topological surface are all the same thing. But this is also for the purposes of the lectures I'll give. This is an algebraic object. Okay, and object here really means a Deligne-Mumford stack, but I'm just going to pretend it's a variety for basically the entire time. Okay. Okay, so maybe that's a good place to start. So why is this object algebraic? So why? Okay, where does the algebraic structure come from? So this is really so maybe one of the things that makes this object mysterious is that it's the moduli space of abstract Riemann surfaces, right? These Riemann surfaces are not embedded anywhere. They're not presented to you in a favorite way as a vanishing locus of some polynomials, right? That's what makes it difficult to understand all of these objects at once. And so really where the algebraic structure comes from at some point is that algebraic geometers are very good at constructing moduli spaces of embedded objects, okay? So embedded, let's say genus G degree D curves in some projective space, ER, these have a good moduli space. I shouldn't say the word good. Good has become a technical term. So maybe I'll say a natural moduli space. Okay, so why is this? So this is what is known in our world as the Hilbert scheme. I should say, partly what I'm trying to do in the first 15 minutes of this lecture is get a sense for where everyone is. So I'll just ask, who here has seen the Hilbert scheme before in some context? Okay, that's sort of what I'd guessed. Okay. So that's absolutely fine. Okay. So this is so what do I mean by this? So there's a natural space, an algebraic variety essentially, or a scheme, whose points are in correspondence with embedded degree D, embedded genus G curves put in projective space by degree D, put in projective space with degree D. And so where does the structure of this moduli space come from? Well, you see, if you have a curve inside projective space, it has an equation. The equations are captured by some kind of ideal. inside a polynomial ring. I guess I'm working over the complex numbers. So it's captured by an ideal inside of a polynomial ring, and you see there's some structure here that you can actually keep track of. This is a submodule of the polynomial ring, but in particular, it's also a linear subspace of this vector space. This is an infinite dimensional vector space, but if we between us only agree that we have to care about polynomials of degree up to 10 billion, then it's a finite dimensional vector subspace of a finite dimensional vector space. And so you get a connection here. So by kind of truncating the polynomial ring, you get a connection to the Grassmannian. And this was one of Grothendieck's great insights, is that if you want to parameterize embedded objects, really what you're parameterizing is ideals, and if you truncate the ideals at some high enough degree value, okay, this needs me to fix these two numbers, but if you truncate the ideal, you'll get a finite dimensional vector subspace of a vector space, and that will give you an interesting map to the Grassmannian, so you can try to realize this set as a subset of some Grassmannian. We know this is algebraic, and so you can at least ask the question, is that subset defined by polynomial equations? Okay, so ultimately, this is where the algebraic structure comes from. Okay, so we're still here in this realm. So this is, I still need to say something about abstract curves. So the next step is kind of extremely classical geometry, which is, okay, sorry, I should have said G is at least 2 for most of this, okay, for a while. So the genus will be at least 2. So the second fact that you need to know once you've built this object is that every genus G curve, let's say C, has a, it's smooth, so it has a cotangent bundle. Or maybe an algebraic geometer would say a sheaf of one-forms. And so the sheaf of one-forms is, okay, this is some kind of bundle, maybe I'll call it omega C, on C. And so it has a space of sections, okay? So if I look at it, the space of globally defined one-forms, this is a G-dimensional vector space. And if I choose a basis for this vector space, plus basis, then what you get is a basis of interesting one-forms on a curve, okay? Interesting differential forms on the curve. And so as an outcome, you get a map, okay, it turns out to actually be a map, to project a space after a choice of basis. Okay. So for this reason, or for some other reason, we tend to call this the canonical bundle. Okay, these are all the same word, in at least for smooth projective curves. Okay, so so what does that mean? It means that every genus G Riemann surface can at least be mapped to projective space essentially in a canonical way, where the word essentially is eaten up by this choice of basis. Right? Okay, so for technical reasons, again, not essentially classical algebraic geometry, it's morning time, so I'll ask some questions to make sure we're all awake. Once you have an interesting map to projective space, you should ask yourself, maybe, is it an embedding? That's the first question you should ask. And this is not always an embedding. So does someone want to venture out? When is this an embedding, or when does it fail? When does the canonical map fail to be an embedding? So base point free, that's actually automatic. So it fails to be an embedding in an actually interesting classical situation. So if C is hyperelliptic, but thank you for volunteering. If C is hyperelliptic, then this fails to be an embedding, fails to embed, but otherwise it's okay. Okay, hyperelliptic curves in the classical geometry of curves are often extremely special, but so nevertheless, if you kind of ignore this, this is a relatively small case. It eats up everything in genus 2, but it tends to have it's relatively few curves. In general, it fails to be an embedding. Okay, so this is not such a big problem. So as a consequence of this, it's better to use another line bundle, which is some tensor power of C. Okay, so it turns out that if once you take R equals 3, this is good enough. Okay, so a consequence of this is that every genus G curve can be embedded. Oh my goodness, that's terrible spelling. Embedded into some projective space by omega c tensor cubed. Okay. So yeah. That's right. Yeah. If and only if. Yeah, so all of this, actually, this entire board, well, all the content in this board is a consequence of the Riemann-Roch theorem. Actually, so maybe that's my second question. Of the people who are not algebraic geometers, actually of everyone, is everyone happy with the Riemann-Roch theorem for Riemann surfaces? Okay. Sorry, I'm being cautious because it's 4 lectures. And so I want to at least have 25% success of having people understand what I'm saying. But by this afternoon, I'll try to make sure you're lost, okay? That's my, Okay, so in what way have we succeeded? Well, every Riemann surface, I've told you, can be put inside some projective space. This n is some predictable number that's told to you by the Riemann-Roch theorem. And it can be, you can kind of stick it in projective space in some canonical way up to a choice of basis, right? And so you're kind of getting closer, because what I've now told you is that somehow every curve is occurring inside one of these Hilbert schemes, and these Hilbert schemes are algebraic things because they're stuck inside a Grassmannian somewhere. Okay, so we're getting there. And so the only issue we have is this up to choice of basis. Okay, so to construct MG, so you do 2 things. You take the locus in the Hilbert scheme of degree D curves of genus G in this big projective space, such that the O of 1, I'll explain this in a moment, restricts omega c. And then 2, take a quotient by PGL, whatever this number is. Okay, so what do I mean by this? So if I look inside the Hilbert scheme of degree D curves of genus G inside a fixed projective space, I know one way to get them is by taking, my genus G curve, taking its triple tensor power of the canonical bundle and then using that to embed. But there might be other degree D curves of genus G inside that projective space that are not obtained in that way. Okay, and the correct condition, the condition that you need, is exactly that the line bundle that has come to you from projective space is the same thing as the canonical bundle on the curve. Right? So that's what you need. So the equality of 2 line bundles is an algebraic condition. The locally closed condition inside the Hilbert scheme, and then taking quotients is an art in algebraic geometry. It's not a perfect science, but this can be done, for example, using the theory of GIT. Okay. And so what do I mean by GIT? Nothing too fancy here. All I mean is that I have some interesting algebraic subset, and it's essentially projective, so it has a coordinate ring, and I just take the invariant function to build as the functions on my new space. Okay, so that is GIT in a sentence. If you want GIT in a book, there's a book. Okay. So, so why start here? I want at least this to have some content, right? So MG, it's an object that belongs to algebraic geometry as well as all the other subjects it belongs to. Okay. My first exercise for you. Okay, the real exercise is just to understand the lectures, okay? But I will give some exercises as well. So the first exercise is to prove that MG is non-empty for all G, at least. Okay, in other words, for all values of G. And depending on your perspective, on your mathematical perspective, there are different ways to do this. If you can do this already in your head, then this question is too easy for you, and the correct question is find 3 ways to show this. Okay. Okay, any questions about that? So we've discovered that MG is basically an algebraic variety. That's where we are. We've still not gotten to MG bar. That will take some time. Okay, so it's an algebraic variety, so we can ask interesting questions about it that we would ask of an algebraic variety. And so maybe the first one is the dimension. What is the dimension of MG? Okay. So there are a few different ways to think about this. The first approach is actually due to Riemann. So this is Riemann's parameter count. And so this is kind of, this is from a famous paper in the early 19th century. This is, what is it? It's a Theorie der Abelzinfunktionen. It's kind of, so Riemann did not write so many papers, but in this one, he does, so theory of abelian functions. It's kind of an amazing paper. One thing he does in this paper is I'll show you one of the arguments in the paper, but he calculates the dimension of MG. So he answers this question. Of course, MG didn't exist back then, right? Because no one had invented the word moduli. So he did that also. He also invented the word moduli. Okay, so how does Riemann think of the dimension of MG? Well, in some sense, the dimension of MG is baked into the thing I told you before, right? If you were able to estimate the dimension of the Hilbert scheme, then you'd win. Of course, that's not how Riemann was thinking about the moduli space of curves. And so he had a different approach. Okay? So this brings us to the idea of Hurwitz theory. So the idea is you study a moduli space, which I'll call MG P1D. So this is the space not just of genus G Riemann surfaces, but genus G Riemann surfaces that are equipped with a degree D map to P1. Okay. So one can also prove that this is an algebraic variety, so it also has a dimension. I'll leave that out. It's in some sense, it's actually easier than the previous case. And so to use this, what you have to do is remember a little bit about the basic theory of Riemann surfaces. So if I have a degree D map on a Riemann surface, it will be branched at some finitely many points, right? Most points will have D preimages, and finitely many points will have fewer than D preimages, and we refer to those as the ramification points of the map, and the images are the branch points. Okay, and so one thing you can always do, so I'll just write here, the branch and ramification data is controlled by the Riemann-Hurwitz formula. Okay, so the Riemann-Hurwitz formula says that in a situation like this, it'll tell you, because you know the genus of the domain and the codomain, and you know the degree of the map, it'll tell you exactly how the map ramifies, okay, or the total amount of ramification. Okay, so what you can do in this situation is the following. Given a map, you can try to keep track of only some of the information, namely the locations of the branch points on the target. Okay. So for example, if G was 0, that's technically not in this stuff we're discussing, but let's say G was 0 and I was looking at degree 2 maps to P1. Well, what's an example of a degree 2 map to P1? Maybe Z goes to Z from P1 to P1. Maybe Z goes to Z squared is such a map. Okay, where does that ramify? Where over 0 and infinity, there's only one preimage, right? And so now you do the calculation and it tells you, okay, Riemann-Hurwitz says that the Euler characteristic, the genus is essentially multiplicative, the Euler characteristic is multiplicative, and then there's a correction term, which in this case is exactly equal to 2. Okay, so in that case, you would keep track of the 2 branch points, which would be 0 and infinity. Okay, so this is our points, our unordered points on P1, symmetric power of P1. Okay, so maybe I'll call this Burr for branch map. And so there's something beautiful about the branch map. In fact, the branch map is finite, I guess, when non-empty. I'll just leave it at that. I don't want to think about whether finite empty set has a finite map or not. Okay, so this branch map is finite, so that says something geometrically very beautiful. It says that if you fix the locations of the branch points, and you don't know the domain curve, you can reconstruct the domain curve up to finite choice, right? This is a very simple fact, actually, from complex analysis. It just says that once you delete the branch points, it's a topological covering space. There is essentially a unique complex structure on P1, and so you get charts for a complex structure on the domain. And then Riemann tells you the sort of removal of singularities that you learn in complex analysis tells you that you can remove the singularities. Okay, and then you get this up to finite choice. The finiteness has to do with the monodromy. Okay, so it's just purely topological data. Okay, so this branch map is finite. This is an exercise if you don't know this already. So if I give you a curve and a map to P1, you can remember basically what's going on the P1, but you can also remember basically what's going on the domains, or just the domain. So you can also go to MG. Okay? So given curve with a map to P1, I either remember the P1, namely the branch points on the P1, or I remember the domain curve. Okay? So the second fact we need is that the source is surjective once D is sufficiently large. Okay? So this is easier to prove. This is actually another consequence of the Riemann-Roch theorem. Right? Every degree, okay, because actually, I guess this is only because of the way I've set it up. But every genus G Riemann surface, every genus G algebraic curve has a non-zero meromorphic function on it of degree D for some fixed D. Right? You can get all of the genus G curves by some fixed D. Okay. For example, you can use the canonical bundle. Okay, so this D I think is roughly G. It's roughly half G. That's what you need D to be, but it's not important for us. Okay, this is just for some large. This is an easier exercise. Okay. So I want to estimate the dimension of this thing, right? And so how am I going to do it? This is a classical argument in algebraic geometry. I'm going to try and figure out the dimension of this thing, right? And that's easy because that's just R. Right? So I know the dimension of this. This is a finite cover, and so I know the dimension of this. And now once I know the dimension of this, if I can estimate the dimensions of the fibers of this map, namely for every genus G algebraic curve, how many ways are there of putting, of mapping it to P1, then I win, okay? The strategy is to study the fibers of this map. Okay. So how about, dimension of a fiber of source. This is also straightforward to calculate because this is just asking, okay, so to do this, if you want to build a degree D map from C to P1, what you have to do is the following. So you have to first choose a divisor up to equivalence or a line bundle on C of degree D. Okay, and this is well known. There are G moduli for doing this. G moduli for this. And then two, you have to choose, I guess, two sections of this line bundle. Okay, and there are, for D large, there are degree of the line bundle minus G plus 1 many ways. Okay. Again, let me just check in. How painful is this sentence for people? Okay, a little bit. Anyone find this confusing? Yeah, I know what to say if you say yes, so just tell me if you find this confusing. No, okay. Great, okay, so I actually claim we've won now. Okay, we've won. So the number of branch points is told to me by Riemann-Hurwitz, and so I know this dimension. I know what R is just in terms of D. Okay? So you have to assume the simplest possible ramification for this to happen, but nevertheless, we know what this dimension is. And so that means I know what this dimension is, and then I also know the dimensions of the fibers, because for D large, that's just given by this. So this is Riemann-Roch. And then, so I take G moduli for choosing a line bundle, and I choose two sections of that line bundle to give me the map to P1, and that's basically everything. Okay. And so there are some numbers here, and actually, okay, so the exercise is to do the arithmetic. So deduce from this that the dimension of mg is 3g minus 3. Okay? Here? This is very large, sorry. A degree minus g plus 1 many moduli. Degree of L. This one? Yeah, sorry, this is the line bundle that is giving you the map. Okay, so maybe I say it like this. Choose a divisor or line bundle L on C. That choice is G dimensions worth. And then once I've chosen that, sorry, this degree is the same thing as D. It's better to say it that way. D minus G plus 1. Okay, so you know all the numbers, and I just haven't put it together for you to actually do the calculation. Because if I do it on the board, it'll be wrong. Okay, so that's why you call it. That's how, for those of you who are young, that's how people invent exercises. Okay, okay, so this was Riemann's parameter count, so now we know at least that this space exists, and it has dimension D, dimension 3g minus 3. Okay, a second way is to think about the dimension of the tangent space. So let's say we have a point in mg. So a point in mg is just a genus G curve. And then we can consider the tangent space to mg at that point. Okay? And if we were to calculate the dimension of this, that would give us some control over the dimension of mg itself, right? So maybe you have to be a little bit careful about that on general grounds, but okay, it's going to work out. So at least we're calculating the local dimension. Okay, so what is this? So you see, mg is a moduli space. It's not just some random variety. Its points mean something, and so the tangent space also means something. Right? So what the tangent space really means, so a point of the tangent space. Sorry, see, mg is a first order deformation of the complex structure on C. Okay. So this is a little, maybe this is slightly more sophisticated, but I'll try to walk you through it. Okay, so what do I mean by a first order deformation of the complex structure? Okay, so now I sort of have to be an algebraic geometer because I want to say it this way. So to an algebraic geometer, the tangent space to anything is just solutions to the system of equations that defines that thing, but over this ring, C epsilon mod epsilon squared. So this is kind of the role of a tangent vector in algebraic geometry. And so this is kind of an elementary thing. So I have this algebraic, you imagine this algebraic curve. It's given by some equation, and you want to deform the equation, right? You're imagining that epsilon is really some small number, and you're trying to perturb the coefficients of those defining equations until it moves. And so how do you? So you just want to understand basically the set of all these things. Okay, there's some technical words I'm supposed to put in here. These should be flat deformations in the module theory sense. So the functions here should be a flat module over this. I guess when I set epsilon equal to 0, that gives the original C. Okay. But nevertheless, if I just think about it as a set, right, I should be able to build these in an extremely concrete way. So, how do you build such a thing? Well, you can do this by gluing data for deformations of open covers. Okay, deformations of opens in a cover of C. Okay. So what does that mean? So I have my Riemann surface. And I imagine taking some kind of open cover of it. Okay, so this is U1, maybe this is U2, etc. So I cover it by these opens. So it's important for what I'm doing that I work in the étale topology if I'm an algebraic geometer, or in the classical topology if you're a normal person. Then okay, so there's the overlap. So what's the idea? So there's a fact, which is very useful fact, that locally all deformations of complex structure, deformations, are trivial. Okay, so if I have a kind of local piece of a manifold, and I kind of try to wiggle the coefficients, nothing will happen locally. Okay, so what I mean by trivial here is I take this UI, and if I kind of follow what's happening to the UI, restrict the functions to just the UI, it will just be functions on UI cross functions on the base. Okay, so it'll just be whatever ring I had R tensored up with C epsilon 1 epsilon squared. Okay, so this is just a fact. So this is what this is using is the smoothness. So a general slogan. So this is just some fact about the polynomial ring. Okay, I'm not giving you the details, but it's not hard. So if I have a one-variable polynomial ring, you can imagine that I can try to build objects like this, and so this is purely algebra. That's some concrete way to do this, and they'll just all be trivial. Okay, they'll just all be isomorphic to the trivial thing. Okay, so locally on each open, my deformation is completely trivial. So it's just a question of how I patch together these trivial deformations. Okay, yes. So yeah, good question. So we're deforming, not degenerating. So you should think about it as I start with, here's the fact that I think will help. If a polynomial if a coefficient is 0 and I deform it a little bit, it will, if it can become non-zero. But if it's non-zero to start, and if I deform it a little bit, it stays non-zero, right? An algebraic way of saying that is mod epsilon, it's what I got originally. So if it wasn't 0 after I mod up by epsilon, it's still non-zero. Yeah, you can't set things equal to 0 by doing this. Because of this condition, okay? When I set epsilon equal to 0, I get the original. Okay, so all the deformations are locally trivial, and so I just have to understand this kind of gluing data. So what is the gluing data? Well, if you imagine what's happening on Uij over here, U1, 2, for instance, well, now you think about the first time you learned about manifolds, right? So I have some trivial deformation here, right? And so I can express that trivial deformation on one chart or on the other chart, and the difference will be a sort of change of coordinates, right? And so what do I get on each Uij? I get a sort of infinitesimal automorphism of the complex structure. Or in other words, I get a section of the tangent bundle. Okay, which is fancy speak for vector field, right? So locally, this gives me a vector field. Okay, and now you have to think a little bit more. So for those of you who have seen sheaf cohomology, this will be straightforward. Otherwise, this is just a slogan, I guess. So this is just, almost by definition, H1CTC. Okay. So anytime you have an open cover and you have a section of some sheaf, like the tangent bundle, on the double overlaps, subject to some condition on the triple overlaps, you automatically get an element of H1 this way. Okay? And so how has this helped? Well, I've just told you that the tangent space to the moduli space of curves at this curve is naturally identified with a vector space, a natural vector space, whose dimension is predictable, okay? And so the exercise, yes, another exercise, is to show that this number is indeed 3g minus 3, and you do that by the Riemann-Roch. Okay, so I think that's the 5th appearance of Riemann-Roch, what I've said today. Exercise. So I show H1 CTC has dimension 3g minus 3 for all C. And then you can deduce from this that MG is smooth. Okay. About half an hour, right? Left? What we see. Yeah, that's fine. I'll still finish in half an hour. You know, there's coffee and yeah. Okay. Okay, very good. So hopefully that gives you some sense. If this stuff didn't make sense, then that's probably okay. I'm not going to lose you immediately. Yeah, that's a great point. So right, so the comment is what? That I said it's an algebraic variety, but it's not smooth as an algebraic variety, so how could it be smooth as an algebraic variety? Of course, yeah. So that's fair enough. I didn't actually say that MG is an algebraic variety. I said that I'm not going to distinguish between the words algebraic variety and Deligne-Mumford stack. So in some sense, you know, I don't mean to belittle the theory of Deligne-Mumford stacks. It's extremely important. But one of the beautiful aspects of the theory is that you can basically ignore it and it will be okay. Okay, that's a feature, right? That's how you know it's a good piece of mathematics, is you basically get all of your theorems for free. So more seriously, what the point is of this kind of Deligne-Mumford stack stuff is that you always think about the moduli problem, right? So you never think, here's something you almost never do unless G is small. You never think of MG as being given by a particular set of equations in some projective space. You never think about that. That's just not something you're supposed to do, right? In fact, I basically don't know a single example where you actually do that. And so the point is, the fact that it's an algebraic variety is not being used. What is being used is that the points mean something, right? So if a map from some other variety to MG is something that means something. And so you see, when we calculated the tangent space here, what I really said is that, you know, the tangent space to this thing, whatever it is parameterizing something, right? So I'm constantly using this moduli interpretation, and that's just a way of saying I'm working with the Deligne-Mumford stack. Okay? So I'm working with the functor of points or something like that. Okay. Yeah. Any other questions?
Like at the picture you said you work in the type of the is there like any instruction we can
So yeah, I think the point is this is a little bit harder to see. So, sorry? It's true, yes, it's just, yeah. Yeah, that's right, it's fine. I think that's right. I think that's right, yeah. So at least the way I think, I think maybe I'm saying how I think about it. The way I think about it is that given a polynomial ring in one variable, in some variable t over the complex numbers, if I want to turn it into if I want to look at all flat deformations of it, namely ways of turning it into a module over C epsilon, then that's something that by hand you can show that there's only the trivial way to do that. Everything is isomorphic to the trivial one. I think it's probably true. Actually, no. So that's true only for a polynomial ring in one variable. I'm not sure about the Zariski statement. I'm a little fuzzy on that. Is it true that every Zariski open subset of a deformation? Yeah, maybe that's not true, actually. Yeah. Sorry? État locally or Zariski locally? Yeah, okay. Yeah, okay. Is that right? You can just, yeah, fine. Okay, yes, thank you. Great. Okay. So, any other question? So I now want to state a lemma. Yeah. 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 Yeah, so the problem, so that's a good point. The problem is that doesn't, right, so I'm trying to do this in a way. So yes, that's another way to calculate the dimension of mg. Maybe what I'm a little bit more careful about is that, what are those? That's a gluing construction, right? And so does that tell me that the tangent space of mg, the algebraic variety is, it's not obvious that those tangent spaces are the same, right? You're using the fact that a hyperbolic structure not only is the same as an algebraic structure, but also that the deformations of the hyperbolic structure are the same as the deformations of the algebraic structure. There's something to think about there. Yeah, if you're kind of hyperbolically inclined, then yeah, there are other ways to get this number. This particular approach will be relevant for us a little bit later on. Okay, so the lemma I want to state is kind of an elementary fact about mg. Our next fact about mg is that mg is not proper, okay, i.e. not compact in the classical topology. It's Hausdorff space in the classical topology, but it's not compact. So I think this is a fairly intuitive fact, but it's actually a little bit tricky to give a complete argument here. Okay, so why is it intuitive? Okay, the comment I just got was prescient. So of course, the thinking for why this is true is that if I take a closed loop on this surface and I degenerate it, I kind of shrink it, and I get something like this, which is evidently not smooth, right? So what is the problem with this? Well, it's not obvious you can realize this as a family of algebraic varieties, right? Even though each element, right, so for every possible value of the radius of this circle up to 0, it's realized as a family of smooth projective curves. This doesn't actually prove technically that mg is not proper, right? Because I want to think about this really in the world of algebraic geometry. Okay. So in particular, let me try to convince you that there's something to think about here. So you could take a family that over a generic fiber looks like this, and over the special fiber looks like this. Right? So I can easily engineer a family like this. So for the algebraic geometers, I can take C cross A1 and then just blow up a point. And that will give me exactly this picture. Okay? But this does not prove that mg is not compact, right? So what will happen in this case is that if you try, so what does it mean to say mg is not compact? There should be some direction going off to infinity, right? But if you think about away from this point, there's no variation of the complex structure. So even though this is a family of algebraic curves, or Riemann surfaces, it's actually just the constant family, right? So the map to mg that tells you how to get this constant family is a constant map, and so it's not a direction that runs off to infinity, right? So an algebraic way of saying this is that actually there is that the constant family, I'll just say it like this. This is the actual constant family, and this is a constant family just until it reaches a special fiber. So these two are actually birational. So namely, they're equal away from a closed set, and so they have the same general fiber. And so in fact, that suggests that this is just some kind of useless thing. So of course, if you're a hyperbolic geometer, this should also be familiar, right? Like it's possible to pinch some kind of object here by bubbling off a sphere, but you know that that's not a stable curve. It's not a. That doesn't on its own prove that it's non-compact. Okay. So the proof of this, I'm going to basically again leave as an exercise. This lemma. But okay, it's kind of interesting. So maybe the thing I actually want to say is what has to be proved. Okay. Right. This is a kind of heavily AG perspective. So let's say I have a family over a disk. Okay, and I'll assume, okay, it's just a family, maybe I'll call it pi. Assume pi is smooth, so it's a submersion away from the origin. Right, so it's a nicely varying family. And then let's assume that if I take the central fiber, okay, I want to say basically that it's interesting in some way. And so there's different ways to say this, but let's say assume that no component of C0, okay, actually maybe I say it like this. Assume C0 is reducible into two components, C01 and C02. I'll draw a picture in a second. And let's say the genus of C01 and is greater than 0, and the genus of C02 is also greater than 0. Okay. So how would you get something like this? So maybe your curve, right? So you imagine this is some kind of disk of coefficients, some kind of small set of complex numbers. And so how do I get your curves? Well, maybe you write down a polynomial in P2, homogeneous polynomial of degree D in P2, right? And you mess with the coefficients in such a way that when you set the parameter equal to 0, the polynomial you get factors into two polynomials, right? So maybe if you start off with a degree 4, maybe it should factor into a degree 3 and a degree 1 or something, right? Except not that, because I said this thing about the genus. Okay? So maybe the simplest one to say is I could take a degree 6 curve and break it up into 2 degree 3 curves. Okay? So what's the picture? Maybe. So this is kind of what my, the real picture of what my curve looks like in 1, 2, 3, yeah. And it kind of breaks up into these two pieces. Okay. Okay, this is a cartoon. Okay. So you should convince yourself that such a thing exists. You can just do it by messing around polynomials in P2. Actually, if you do that exercise about proving that there's a curve of genus G for every G in sufficiently many ways, you'll also do this probably. Okay. And so now, what actually has to be proved? We need to show there is no other, let's say, C prime to delta such that, okay, C prime 0, so when I set the coefficient equal to 0 on the disk, is smooth, and C prime agrees with C away from 0. Okay, that's what we actually have to show, right? And again, I encourage you to think about the difference between these two examples when we show this. So here, I've found, even though this was my candidate for something that might show that there's no smooth limit, right? So the point of this is to say there's no smooth limit. So this is a direction that goes off to infinity in the moduli space of curves. What I'm spelling out is the valuative criterion for properness, for those of you who have seen that. Okay, and so I have to basically show that I'm not in this situation. And so in turn, what I need to show is that this condition, right? This is the only interesting condition that I have. This condition somehow gets me out of trouble, right? Okay, so maybe I'll call it use condition star. And then a small piece of algebraic geometry which is the strong factorization theorem for surfaces. Strong factorization theorem for so that's basically the proof. Okay, so let me just explain this last part. So what's going on here is that let's pretend that I had a C prime and a C, right? So the C prime and a C they're the same away from their central fiber, right? They're the same away. This is my C prime and my C. They're the same away from this fiber over 0, right? And so what that means is they're actually birational, okay? They're two birational surfaces. And the strong factorization theorem is a theorem in the theory of algebraic surfaces that says that if I have two birational surfaces, I can get from one to the other in a very simple way. Right? I can get from one to the other by a sequence of blowups and blowdowns. And then the key observation is that blowups and blowdowns only ever create or remove P1s. They only ever create or remove Riemann spheres. And so as a consequence, this can't be the situation that's happening, because if I had a central fiber, I wouldn't be able to ever create genus when I go to the other model. Okay, does that make some sense? Okay, so I know that's probably a unusually long time to spend on showing that something is not proper, but I hope it'll be worth it. Okay. Plus, everyone always says this. It's like, oh, moduli space of curves is not proper because smooth curves can degenerate to singular curves, but that's not actually a proof. And so this is a bugbear of mine, and so I've decided to make you all suffer through it. Okay, very good. So we know the moduli space of curves is not proper. This sounds like negative progress, but at least it makes the next part well motivated. So one of the really important things about smooth algebraic varieties is they can be compactified. Okay, so they can be compactified by a theorem of Nagata. That's a deep fact, but usually it's not a particularly explicit fact. Okay, so the nice thing about the situation we'll be in here is that there's sort of a God-given compactification or a Deligne-given compactification, depending on your religion. Okay, so Deligne and Mumford construct this moduli space Mg bar of stable curves. Stable curves of genus G, which is sort of our main player. Okay, so what is this thing? I'll basically tell you what it is as a set. So it's a nodal curve. Picture. So see, this is a nodal, meaning locally given by xy equals 0 at its non-smooth points, nodal curve. Okay. It has arithmetic genus G. Genus. So this is a singular object, so there are two different kinds of genus. So this is the arithmetic genus, and I'll explain what that means in a moment. And C is stable. Okay. So nodal curve is just an algebraic curve that locally every point is either smooth, so you're somewhere here, or it looks like xy equals 0, so quadratic singularity somewhere here. The genus of such a thing is, okay, so it's the, yeah, okay, it's the arithmetic genus. All right, I'll explain what this means in a second. So in this case, let me just say what it is. So the genus of this curve. Okay, what should it be? It should be the sum of the genera of the components. Okay, so that's 2 plus 1, 3 plus 1, 4. But then you see there's a kind of hidden genus all the way around here. So that looks like 5. And this is how you do it in general. You kind of add up the genus of the components, and then you look for the hidden genus that's kind of in the loops that have been crushed. Okay, so that's how you calculate the arithmetic genus. When I talk about dual graphs in a moment, I'll say this more precisely. Okay, so that's the genus. C is stable just means that the object has finitely many automorphisms. Okay, so what that means in practice is just that every P1 component, so every component that's a Riemann sphere, every P1 component meets at least 3 other components. Okay, or in the lingo, every P1 component, you see that this is a P1 that I've drawn. Every P1 component has 3 distinguished points, 3 points that don't look like any other points, right? And so that has finitely many automorphisms because it kills the Mobius transformations on P1. Okay, technically I should say something about genus 1, but I think it's basically that. Maybe I say connected here. Okay. This thing? No, that's stable. I don't think I've said anything that has prevented that. So here's one point, here's another point, and here's another. So maybe you're worried about automorphisms off the elliptic curve. Yeah, that doesn't come into it. Any other questions? It's kind of a crucial concept, so we should make sure we get this. Okay. Thank you. Yeah, that's right. G is still at least 2. Yeah, G is still at least 2, but I'm allowed P1s and elliptic curves inside. It's just the total genus has to be at least 2. So that turns out to, I know, I think whoever's seen this before is expecting a second condition here, but I actually don't need it yet, if you think about it. Okay. Okay, so part of the reason I spent all of this time on convincing you that MG has an algebraic structure is because this time I really can't do much to convince you that I can state a theorem. So the theorem is due to Deligne-Mumford, but also a key part of what I'm saying, I guess, is due to Gieseker. So MG bar is an algebraic thing, okay? Maybe I'll just say it. It's a Deligne-Mumford stack with projective coarse moduli space. Okay, which feel free for these lectures at least, and maybe for the rest of your life, feel free to read this as MG bar is a projective algebraic variety. That's what the sentence is saying. Okay. Okay. So it is smooth. It is smooth. Such a shame to put such a cool theorem at the bottom of this. Cool. It's a smooth space, which is great. MG inside MG bar is dense. So I'm only adding just a very small amount to make it compact. The complement MG bar minus MG is a union of pure codimension 1 subspaces, whatever, sub-varieties, substacks. And what else do I want to say? Okay. Maybe the last thing I'll say is there is a universal family. This was true also in the MG case. C over MG bar. And so what is this universal family? Well, I'll tell you what the fibers are. The fiber over a point called C is C. Okay. Okay, so this is meant to be the thing that parameterizes all stable genus G curves. And so in particular, over a point corresponding to a genus G curve, it should be that genus G curve table. Okay. This is our main character. So let me just say a word about how this is constructed. So the history here is quite interesting. So Deline and Mumford, okay, they were interested in a particular geometric question. So MG had kind of been around in various guises. Maybe its coarse moduli space had been around. And so what these guys invented was the notion, obviously, of a stack. And they proved that MG is a stack, okay? And so basically the content of that theorem is that it's what I've been saying, is that it's very close to being an algebraic variety. And you can more or less treat it like an algebraic variety for many purposes. But also, you know, things like the word smooth and irreducible and these kinds of words actually make sense for this object, right? It's not just something random. Okay, and so they proved all this stuff. And so Giesecke gave a construction of this space that is pretty much the construction that I gave you of MG. So what I said for MG is think about a curve, embed it into projective space in the canonical way, choose a basis, okay, triply canonical way, choose a basis, mod out by group action after taking some subset. You could do that with MG bar, okay? It's just so sort of infinitely harder, okay? You have to take the 5 canonical embedding given by the dualizing sheaf of omega, the dualizing sheaf omega c of the curve, and then you have to perform some extremely subtle GIT analysis to show that at the end of the day, the only things you get are really the points of MG bar. Okay, so that's an amazing paper, an amazing result, and basically the two together tell you that you can pretend it's a smooth projective variety. I will say something about what goes wrong, where the stack stuff gets involved, but probably not yet. Maybe in a minute. Okay, so there's a couple of variants that I want. Oh, maybe this is just one, actually. Yeah, just a variant. This is MGN bar. So this is just the same thing, but I also, in addition to my actual curve, I have n distinguished points, n pointed genus G stable curve. And the definitions change slightly here. Let me just highlight the changes. So n pointed means that I have chosen P1 through Pn on the curve C, lying on the smooth locus and distinct. Okay, so you're not allowed to choose for one of your n points in, let's say, MG2, you're not allowed to choose for one of your 2 points in either of these nodes, okay? And then you can't choose the same point. Okay, so that's what the word n-pointed means. And, okay, the word stable, well, it still basically means the same thing. It just means that every P1 has at least 3 distinguished points, namely points that you can name. Okay, so what does that mean? Either node or a marked point. Okay, so for example, I could just take P1 with a bunch of points on it, P1, P2, P3, P3, P4, P5, and that counts. Okay, that's now a stable curve. And so this allows me to relax the numerics here. So of course, G is at least 2, N is anything is fine. But then also G is equal to 1, N is at least 1 is fine, and G is equal to 0, N is at least 3 is fine. Okay. So those are the allowable numerics. Sometimes in the literature, you'll see this as MGN bar, G and N are such that MGN bar exists. Okay. So, sorry? The curves are connected, yes, absolutely. So this definition is the same as before. Okay, smooth, n-pointed, stable, connected. I think connected is a prerequisite. N-pointed, stable curve. Yeah. You could also consider disconnected curves. That's fine, and they will actually come up sometimes. Okay, I have a couple of minutes left. So why do we care about this? Well, that will become clearer in a moment. So this is just the complete picture, right? This is just somehow, even if you're not interested in these MGN bars, you see, when you go all the way, when you go deep into the boundary of MG bar, you're quite likely to see, for example, a P1 with 50 other curves stuck onto it, right? So there is M050 hiding inside the boundary. Right? And so if you want to study this, so one of our goals will be to study these kinds of structures recursively in the genus, right? Or to see what structures they form when you put them all together. And you just can't do that without inventing this, right? So this is just the correct level of generality. This is not just for fun, but it also is fun in the sense that these small guys, this genus 0 situation, this genus 1 situation, are some of the are basically the two places where we understand something, everything almost completely. Okay. I think already in genus 2 there are questions that we really don't know the answers to. Okay. Our main object of study this for the remaining time will be, well, I'm interested in this object, which is the cohomology ring with rational coefficients of MGN bar. Okay? So I'm particular here about saying rational coefficients, although I will stop writing it pretty soon. I'm particular here about saying rational coefficients because this is one place it actually matters that this is a Deligne-Mumford stack and not a variety. Okay? So if you try to put Z over here, the fact that this is a Deligne-Mumford stack will mean that the cohomology will be rather weirdly behaved. For example, it will never vanish. It'll just keep, it will, you know, you can go up sufficiently arbitrarily high in degree and you will find non-zero cohomology groups. Okay. So this is our main object of study. And our approach, I'll just say this and then I guess we continue in the afternoon. The approach will be to use the natural recursive structures. For example, you know, given MGN, I can forget one of the marked points and go to MGN minus 1. And there is a morphism that does this. Okay, you just drop the last point, and then if there's anything unstable, you just remove it. And then you go to MGN minus 1 bar. Another thing you can do is you can go from, you know, MG, let's say G1, 1 cross MG2, 1 to MG1 plus G2. So how do you do this? Well, maybe here's your genus G1 curve with a marked point. And here's your genus G2 curve with a marked point. And so you can just smush them together to get a, I'm not going to draw it. Okay, that's not. And there are various variants of this. For example, you could take an element in MG2 with 2 marked points and then glue the 2 points together, right? And that will increase the genus by 1. Okay? So what the point of all of this is that these spaces, all of them together, if you take all the MGN bars together, they don't just live in isolation, right? They're this kind of extremely complicated network of maps that come from forgetting things and gluing things, and I guess those are the two things, forgetting things and gluing things. Okay? So if you want to say this kind of precisely, there are many people that like doing this. You know, one way to say this is the sentence, the collection of all MGN bars together form a modular operad. That's one way of saying this in a kind of algebraic language. Okay, but the way that I'll be using it, I'll just have interesting maps between these algebraic varieties. And so, of course, interesting maps between algebraic varieties lead to interesting maps between their cohomology groups. And the collection of all of these together is what will define. So the outcome of all of this will be this object that's called the tautological ring of MGN bar. Okay? And so my goal is to tell you some things about the tautological ring. That's kind of my goal for these lectures, and we'll use Gromov-Witten theory to do it. Okay, so let's stop there.